excited about this. I've been looking forward to this conversation for months since we were introduced to Dr. Dennis Whyte and his work at MIT. Dr. Whyte is the Director, Plasma Science and Fusion Center. He is Hitachi America Professor of Engineering, Professor and Head, Nuclear Science and Engineering, Massachusetts Institute of Technology, MIT. Having a conversation today with Dr. Whyte and asking questions that we're all so curious about regarding his groundbreaking work is EMA board member Drew FitzGerald. Drew is one of the co-founders of JUST, a company formed to drive positive social and environmental impact in everyday items while creating sustainable awareness around energy, food, and water. He's one of the founding advisors of the Prime Coalition and serves as the creative director for the School of Civil and Environmental Engineering at MIT and creative advisor to the MIT Plasma Science and Nuclear Fusion Center. I gotta just say, it's good to know people. Like, having these two people have this conversation is amazing. Please welcome Dr. Whyte and Drew FitzGerald.
Good to see you, Dennis. Hi, everyone. We're going to get you excited about something that is going to be kind of new to everyone. So we're going to talk about fusion, and Dennis and I have known each other for a little over 2 years. And one of the things, Dennis is super, super humble. And one of the things you could say as a career achievement by yourself is to say, I'm the department head of the nuclear department at MIT, arguably the most progressive in the world. And Dennis would be very humble, and he's going to be here for 2 days, and feel free to go and talk to him. But when you learn when you go there is that there are black and white photos on the wall of people that were working in nuclear physics and applied physics in the 60s and in the 70s. And they're almost coming on a half a century of people that are committed to getting to where we are now. And what we're going to talk about today is a crowning achievement, not just for MIT and not just for the community of applied physicists and nuclear physicists, but it could very well be a crowning achievement for mankind overall. And so with that, I'm going to put it to you, Dennis. Tell us, what is magnetic fusion?
Right, thanks, Drew. So fusion, it's simple. It's actually the power source of the universe. The way that stars work is that at the center of stars is extremely hot. They're basically big balls of hydrogen, which is the most abundant element in the universe. It's about 15 million degrees, and at that kind of temperature, with the high energy of the particles involved, they can actually fuse together to produce helium. Stars are basically large converters. They convert the potential energy, which is in hydrogen, into helium, and by this way, they're able to power stars for billions of years. Our idea is that we actually bring the power of stars to Earth. It's in fact, I just recently visited Rockefeller Center in New York with my daughter was doing a college tour, and they have that great statue of Prometheus, and I took a lot of pictures of it because I realized that myth has been with us for a long time of bringing the power of the power of the fire of the gods to humanity, and in many ways that's what we're attempting to do. We are bringing in many ways superstars down to Earth, and that's our goal, is to make abundant, clean energy forever for mankind by this process.
And that's
just that.
Yeah, yeah. That was just before lunch.
Sorry, that was my not so humble part, I guess.
Right. That sounds so abstract, and it's very hard. You're going to bring the sun down to Earth. Yeah. So, what does it look like? And we're going to.
So what it looks like is actually pretty simple. What we build is it is actually.
Wait, Dan,
trust me,
it's not that simple.
It's actually kind of at its heart, it's simple. Is what we do is we basically we trick this star into not knowing it's on Earth. So what we do is we build a magnetic bottle that's in the shape of a donut. We use very strong, powerful electromagnets to make a magnetic field that essentially holds the star in place without physically touching it. And this is what it looks like. You can see this is the interior of our experiment. This is in the middle of the MIT campus. By the way, anybody comes to the Boston area, please give us a holler. We love to give tours of this. This is how Drew got hooked on this.
Well, it was built in an old cookie factory, so I was going there for that.
It's the Nabisco. It's literally the Nabisco lab laboratory. We recycle at MIT, Nabisco Laboratory, and that's and you can see it. That you can see this is one of my. In fact, it's one of the co-founders of the company that I'll describe a little bit later on. Inside of that device, it's quite compact. And when you look at such a small thing, you just go, how could a star ever fit in that? Well, in fact, where he is, in fact, routinely exceeded the temperature of the middle of the sun, about 100 million degrees, and actually made fusion reactions copiously. But it's a science experiment. Right. And in fact, our goal is actually the thing that's up in the upper left quadrant. You see that device that powers a small city by fusion power.
And one of the biggest things to point out is the human icon to show the scale.
Yeah, exactly.
Scale is a major component to this.
Exactly.
Considering what the challenges we have to face and the strategy MIT's taken. So when we hear fusion, usually you hear the word nuclear before it, and that freaks people out. Mm-hmm. What is the connection with nuclear energy, fissile energy, nuclear energy, and magnetic fusion?
Right. So they're actually literally the opposite process to each other. So fission is the process by which the largest, most unstable atoms or nuclei fission or fall apart. We trigger that, and this is a copious source of carbon-free energy. But as we know, that there are other challenges that come with the use of fission, which have to do with its use in weapons and long-lived waste products. And so fusion is literally the opposite of it. It happens at the other end of the periodic table. It takes the lightest elements, the most abundant hydrogen, and fuses them together and provides emission-free energy. The reason that we pursue, it's harder than fission because it has to happen at about 100 million degrees, which, by the way, and everyone looks at us then like we're crazy at that. That's actually we got that part already. But it actually relieves the other parts which are concerned, particularly if we want an energy source that scales for our entire civilization, which is what we want from a clean energy, compact energy source like this, is that it does not have a role or it cannot be used in weapons, it has no long-lived waste products, and it is inherently safe.
So if there's on Albany Street where this is, if there's an earthquake or a car crash.
Right, so you think, so why does MIT let me build this thing that gets 100 million degrees in Albany Street? It's because it's a little counterintuitive, but it's actually, remember I told you that the reason that we build that magnetic bottle is to trick this plasma into not knowing it's on Earth. And this whole it's hard to, somebody in one of the previous panels, it's hard to sort of conceive of like $200 billion. It's also hard to conceive of $100 million, something that you could almost reach into and get like that, but you can't do that. Because any kind of intrusion from the external world, which is at room temperature, immediately brings it back down to room temperature. All fusion stops. It literally just turns back into a regular gas.
So 100 million degrees to room temperature.
Yeah. So, and one of the reasons is there's very, very, very few particles in this at one time. And in some sense, fusion is a very bizarre energy source, is that we think of energy sources of having lots of fuel or accumulate fuel and do it. It has almost no fuel inside of it at any time. So literally a person breathing on this will extinguish it.
Wow.
Yeah.
So I want to set up a little, a lot of people know, or many have seen, this is the Intergovernmental Panel on Climate Change. Pretty universal scientific trajectories for if our behaviors, if for business as usual. This is an outline of our century ahead if we don't change some things. This is a real deal chart, right? This is why we are all here today. And so when you talk about this has been called the Holy Grail of energy. What informs your daily passion, work, your students, postdocs, PhDs,
right,
about this chart?
This chart is as scary as all hell. If you're a scientist, you look at the trend of this, it's very hard to escape. It's impossible to escape, actually, this chart. And what this says is we need massive deployment of carbon-free energy, like as fast as we can. So where does this lead? To me, it's a moral imperative. It's actually not even just about this chart. We know that we kill millions of people prematurely every year by burning fossil fuels. But we also have to be, as a scientist, like I'm a nerd, I like numbers. You look at the numbers of this, it's daunting. I mean, what we're looking at is it's changing. 85% of our energy use comes from fossil fuel. This has to basically go down to near zero in a very short period of time.
And you feel as though this is one of the greatest hopes to get there.
And this is one of the greatest hopes to get there. It's just because it's such a large transition, such a large translation. And what you want is basically what we call civilization scale energy, namely, and so why do we pursue fusion? So it has limitless fuel. It has fuel that will last for hundreds of millions of years of our civilization. It is, as I said, it's inherently safe, but it is also scalable, which means that once you get this to work, your ability to deploy this into our present energy systems to both make electricity, to make fuel, is almost limitless because you don't have to reinvent that enormous infrastructure. So that's what we think.
Explain how we have limitless fuel.
Yeah, so it's hard. So where does the fuel come from? So it actually comes from seawater. You actually extract very small amounts, relative amounts of water. This is for the deuterium, which is the heavy form of hydrogen. Is about 1/5000th of all the hydrogen. You're drinking deuterium right now with that. There's some of it in there. And it's hard to describe almost. So actually, the deuterium that is inside of this bottle powers a person for a year by fusion. And the reason for this is because you're releasing this staggering amount of energy by triggering the fusion reaction itself. We also use lithium as the other fuel, but this isn't lithium like. So one of the analogies you say. So if you took the lithium from 1 Tesla battery and you use it in a device like this to produce energy, it actually produces enough energy to power 300,000 Tesla cars.
Wow.
Yeah.
So obviously there have been a lot of people. This is a race, and there's some other players in the field. And there are varying opinions, and we've learned and discussed them a lot. Yeah. Give us an example of who else is in the field.
So this has been going on for a long time. We discovered how the stars worked in the 1930s. Almost since then, people have dreamed of how can you actually make this work on Earth. And so really almost the entirety of the world's governments are working on this. They're pushing towards this. And this is a project that I actually worked on for most of my professional career. It's being constructed in the south of France. It's called ITER, with my French accent. You can see it up on the top there. This is a large scientific collaboration among most of the industrialized nations of the world. But it is, and so that indicates to you about how serious people are and other nations are about pursuing this. But there is a problem, and you can see the problem if you look at the time scales which are there, and also the budgetary scales of this,
and the size.
So it really is. It is completely valid. This has been validated by the world's scientific community, not just me, a very large group of people. And the difficulty is that because we've had to do fusion, and this is almost intuitive. Like you don't see a small star around every day. It's just like on Earth, to keep something really hot, making it big is one of the ways to keep it hot. The difficulty is that this led to a situation where a single device was so large it actually required the entire world's industrialized civilization to fund a science project that was going to take 25 years to build because it's so large. And it's you can see the size of the person in purple beside that. It is actually one of the largest, it is the largest construction project right now in Europe.
And that's the image of the actual site plan. And the crane that you're pictured there is the largest crane on the Earth right now.
That is right, yep.
So when you look at that and you look at the trajectory of, it's not in time for climate change.
Right, so, we say the Holy Grail. So, about 5 or 6 years ago, that's what it was looking like to me. The Holy Grail is a very noble quest, but it's always somewhat out of your reach. And this is what it was looking like. Like it was going to be too late. It was too expensive. It's too expensive. You're not going to be able to export this right. And it needs to be economically competitive. This is a theme which I really like here at EMA. Is that it's not just enough to make a new shiny gadget. This has to be economically viable as well too.
So how is MIT making to be anti-ITER or the? Yeah. This synthesis. How are you doing it?
Yeah, so basically it's easy. It's that plot before. It's just like, if you're serious about getting after this, it has to look what it looks like on the bottom. You have to make these devices much more compact, which makes them economically viable, and then you have to produce them and get these rolling out on a much faster time scale. We need this power source by 2030 or early 2030s at the latest, and that's actually what we've done.
And so discuss big, fast, slow, high, low confidence physics.
Right, so did we just make this up? No, we did not just make this up. So this is a quadrant that business people understand. But it's a little bit skewed towards a technologist. The vertical axis is essentially your knowledge of the physics or the science of this. So creating a $100 million contained star on Earth takes some science, takes physics. And what's wonderful about the upper part of this is that the governments did invest the sort of $10–20 billion of fundamental R&D that was needed to get us there. Too slow, though. And the bottom right-hand quadrant is really interesting, particularly based here in the United States, and a lot of it in California, was no. You know what we need? We need smaller, nimbler companies getting after this. And we're going to build ones which we project towards having economic viability. But the problem is that they had to pick things that were not like the upper left quadrant. They had to pick different kinds of configurations. And so we wish them all the luck, but they have a huge amount of physics hurdles to overcome to get there. So we said, no, what we need to do is figure out something that lives in the upper right quadrant. It's fast, small, you can deploy it quickly, but it's based on known science. And we were able to do this with a breakthrough technology, and basically it allows us to take the same physics as in the upper left and make it 100 times smaller. And that's based on the same physics, and cheaper as well, too.
So when I first went to PSFC, I got a tour through this amazing apparatus, and it was just, it was completely new to me. And I was walked through it, and I was so impressed and so excited about it. And at the end of the tour, the fellow took me through, Soren Harrison, said, unfortunately, all this is getting dismantled.
Yep.
Right? And I was like, why? This is sad. This is the most promising thing. This is a half a century of research, and it's getting dismantled because the government doesn't want to fund it anymore. And then I got a call a couple of years later saying, hey, we're still here. Let's talk. Tell me about the near-death experience and why this is a great.
It's one of my favorite lines from Monty Python, The Holy Grail. I'm not dead yet. So we looked at this. So this was, it's interesting when you come to these existential periods. So what had happened? We'd had a 40-year-old, highly successful scientific program at MIT. We'd graduated 160 PhD students. As an educator, this is a wonderful, wonderful place to work. But there was some irony in this, is that we were being closed by the government because we were too small. It's just like, So, we sat back, and so what happened was that, first I went through a pretty bad moment. I just about quit. I just about went off and started working something, because I could never see this coming to fruition in my life. I knew that there had to be something else. I was going to go work in some other thing that would have an impact. And then something changed. What changed was a set of young people. It was my class that I taught. And I sort of had this crazy idea. I took this new technology that I talked about for magnets, and I basically brought this into the class and said, hey guys, you know what? Let's try to do this differently. And then it turns out this is one of my messages for this, is that what we need to do, like our generation, is unleash the creativity and the passion, actually, of our 20-year-olds, because this is more powerful than fusion, quite frankly. And they inspired me. I mean, I was a part of this journey. We brought it up along, and now essentially our very large laboratory at MIT, and you can see some of the people here. This is a small team in fusion, actually, but packed back over there in the left-hand corner is the core of 30-year-olds who are now basically leading this effort, both at MIT and a startup company that we've founded actually to do this.
So from this is going away and this hope is going to be dashed, What happened in terms of you setting the record of coming full circle?
Yeah, so we decided, we found our religion in this, and it was, we were convinced to show the world that actually this pathway of keeping things small, not just in how big the experiment was, but how effective the team was working in a small dedicated team, would be able to do things that you wouldn't imagine that small teams could do. So we worked really hard, and on the very last day of operations, 2 hours before the federal government closed us down, we actually set the new world record for fusion performance in one of the smallest devices in the world that tries to do this.
Yay!
Yeah. It was a bigger whoop than that, I can tell you, in the control room. And you know, this was, to us then, it was the beginning, the launch point. This was, now it made time, it made sense to take this out into the private sector, you know, and the government didn't, you know, only wanted it to be big and slow. So what's fast, you know? Get it out into the private sector. Right. So this is what we did. 6 of us, most of them my previous students, we launched a company and started to go talk to the world, the real world.
And a company that is a consortium of a bunch of different people, one of which is a large oil and gas company. Yeah. That's encouraging, kind of the advanced part.
It's extremely encouraging, yes. Yeah.
So Dennis is going to be here for Impact, and I encourage you to go and talk to him. And I guess we'll close on this is for this group here, this family, EMAs, what can we do? Because it seems so foreign to us.
Yeah, I know. It all looks like Star Trek, something, science fiction. It's not. It's actually, the way I look at it, first of all, it's the people. I have a set of young scientists who could have all gone and made, they're so, I mean, you know them, Drew. I mean, they're so smart, but they're also so dedicated. I mean, you can't believe that they were doing regular jobs, by the way, as postdocs and so forth. We lifted we did $100 million Series A. And that was by the vision and the just extraordinary work of these young people. So the first part is that unleash the young people. And the second one, which I've gained a greater appreciation for, like I said, I'm a nerd, I'm a technologist. Scientists love to believe that science and technology can solve everything, but it's not enough. I mean, you know, the things we do sound incredible, but at the same time, what you have to do is what I say, build the deepest bench possible of talent. And that talent includes people who can communicate this message, like Drew. Drew has been, by the way, amazing in all of this as well, too, as a...
Thank you.
Because he came in and told us how to craft our message. It means a major energy company coming in that delivers energy to people in 68 different countries. This is E&I. It's the Italian super major. They're our first major funder of this. We have philanthropy. We have dedicated high wealth individuals, organizations, some of them that you're seeing around here. This is what it takes. This is a collective effort of everyone coming in, because we're all in this together, and lifting things like this means you need a lot of talent, a deep and round pool of talent that's way beyond the science and technology. And you know, that's one of the reasons to come here, is that I hope you're excited by what you see, because we certainly are.
And we at EMA are constantly going to be tracking this and the progress and identifying ways where you can help, whether you have a science background or you're just a committed and passionate about the mission of EMA and the mission of people like Dennis here. So give a big hand to Dennis Whyte. Thanks.